All right, so for this problem, we are trying to identify some facts about the normal distribution, primarily through the MGF. First and foremost, we want to find the MGF of the summation of the x's. Anytime I don't put the indices and limits of summation, it is understood that I'm summing from 1 to n. All right, so we know that this is equal to expected value of e to the tx1 plus tx2 txn. And when you have a summation and an exponent, that's equal to a product of the original quantities. So e to txi, same thing. Products are also from 1 to n. But this expression of e to the txi is simply our MGF of the original. And we know what that expression is from the formula sheet. It's going to be e to the mu t plus sigma squared t squared over 2. And so we're left with e to the n mu t plus n sigma squared t squared over 2. And our n mu becomes our new mean, n sigma squared becomes our new variance. Thus, our summation and mu n sigma squared. That makes sense because normal distribution stays normal under linear transformations, and then also the mean and the variance are what you expect them to be for the summation of normals. By the same token, we want to find the MGF of T sub n. Main goal here is to piggyback off of what we were able to discover in part A. And so as soon as we can get the expression that we see here as part of this problem in B, the better, right? We want to use that expression somehow in our work here. So I'm going to do this. I'm going to say radical n x bar minus mu times t. Just defining what T sub n is. Okay, from there, I'll rewrite this as, okay, notice that we have e to the minus mu times t times radical n. Those are all constants that we can bring out. So we'll have e to the minus radical n mu t, right? There's nothing random there. The random stuff is all in the x bar. So it's going to be e to the radical n. I'll rewrite x bar like this. Why? Because I want to get that summation of the xi's. And then we'll have the t. Okay, so I'm going to take that t. I'm just going to put it right here. Okay, you'll see why in a second. Anytime you have an MGF, right, we saw over here that the definition of an MGF, both from this and from this, is expected value of random variable times t. Now inside this expectation, I have a random variable times t, lowercase t. Okay. Right, so inside here, we can write that as m sub summation of the xi's. And what we really want to do is leave not just the t by itself on the inside, but everything that's not the summation of xi. Because again, we wanted to exploit that relationship. So we have radical n over n, which is 1 over radical n, and then t on top. Okay. So that underlined expression is equal to this on the right. This leaves us with e to the minus radical n mu t. The MGF, we just use what we had up here, and we'll say e to the n mu, and then I'll replace t with t over radical n. And then we'll have, I'll just write this as a separate E. Okay. We have n sigma squared. And instead of t squared, I have t squared over n now. And then we have the 2 as well. Okay. You'll see that this cancels with this. And you'll see that we have simply a sigma squared here. N's cancel. We just have sigma squared. So at the end of the day, this is just e to the sigma squared t squared over 2, i.e., t sub n is normal 0 and sigma squared, which is exactly what you would expect for t sub n based on what you know. Part C. So for part C, I'm going to find the asymptotic distribution of t sub n. We know t sub n tilde normal 0 sigma squared. There's no n's on the right-hand side. So this distribution is stable. So as n goes to infinity, that's not going to change because there's no n's in that distribution. That's it. Part D. Use the result of C to determine the asymptotic distribution of 5 x bar to the 7th. So in this case, even though we have exact, we also want to exploit because we see a function and we want to use the delta method, right? So if it is true that t sub n is exactly this, it is also true that t sub n, which is this, approaches normal 0 sigma squared because it's already there. All right. Now we're going to let's say use the delta method. Where g of x is equal to 5x to the 7th. G prime of x is going to be 35x to the 6th. Okay. And so what we can say then, radical n 5x bar to the 7th minus, we apply the function to mu, 5 mu to the 7th, approaches normal 0. G prime is 35, and we'll replace the x with mu to the 6th, quantity squared times sigma squared by the delta method.